Welcome to this EWRB Electrical Service Technician Training course. I'm Aria, an electrical tutor working with Roy. In this course, I'll guide you through all the topics covered in the EWRB Electrical Service Technician Exam Teaching Guidelines. Welcome back. In our last lesson, we learned how to test and tag appliances safely. Now, we begin one of the most important technical lessons for electrical service technicians, topic 8.19, electric motors. Because motors have so many subtopics, we'll divide this into two parts. In part 1, we'll focus on the fundamentals, how motors work, their construction, and the different types of single-phase motors. In part 2, we'll move on to three-phase motors, starting methods, speed control, and fault finding. Let's begin with Topic A. Topic A, the basic principle of electric motors. All motors work on one simple principle, the motor effect. When a current-carrying conductor is placed in a magnetic field, it experiences a force that makes it move. In plain words, electric current flowing through a wire inside a magnetic field produces movement, and that movement is mechanical power. This is the heart of every motor, whether it's a tiny fan motor or a large industrial machine. In formula form, the force on the conductor can be remembered as F equals BIL, where F is force, B is magnetic field strength, I is current, and L is the length of conductor. The direction of this force is found using Fleming's left-hand rule. Your thumb points to motion, your first finger to the magnetic field, and your second finger to current. That's the physics behind every turning motor shaft you see. Topic B, rotating magnetic fields. Now let's move to Topic B, rotating magnetic fields. For a motor to rotate continuously, we need a magnetic field that also rotates. This is achieved by using coils placed at different angles around the stator. When alternating current flows through these coils, the magnetic field strength changes with time. Because each coil is out of phase with the next, the combined effect is that the magnetic field appears to rotate around the stator. In a two-phase or split-phase motor, the field rotates at a speed known as the synchronous speed. The formula for synchronous speed is N equals 120th p. Spoken as, synchronous speed equals 120 times frequency divided by the number of poles. For example, a 4-pole motor supplied at 50 Hz has a synchronous speed of 1,500 revolutions per minute. The rotor follows this rotating field, slightly slower, and that difference between the synchronous and actual speed is called slip. Slip is essential for producing torque. Without it, the rotor would just lock to the field and no current would flow in its conductors. Topic C, construction of electric motors. Now let's move to Topic C, motor construction. Every electric motor has three main parts, the stator, the rotor, and the frame. Let's describe them in spoken form. The stator is the stationary outer part of the motor. It contains laminated iron cores with copper windings that produce the magnetic field. The rotor is the rotating inner part connected to the shaft. There are two main rotor types, squirrel cage and wound rotor. A squirrel cage rotor looks like a cage made of aluminium or copper bars short-circuited at both ends by rings. It's simple, strong, and maintenance-free, which is why it's used in most motors. A wound rotor, on the other hand, has three windings connected to slip rings. This allows resistance to be added externally for speed control, mainly in older or heavy industrial motors. Finally, the frame supports and protects the motor. It includes the bearings, cooling fan, and terminal box. Modern motors also include an insulation class marking, class A, B, F, or H, which indicates the maximum winding temperature the motor can safely handle. Topic D, types of single-phase motors. Now for Topic D, types of single-phase motors. Single-phase motors are widely used in homes and small businesses for fans, washing machines, pumps, and tools. However, a single-phase supply alone doesn't produce a rotating magnetic field, only a pulsing one. So, these motors use special starting methods to make the rotor turn. Let's go through each main type. 1. Split-phase motor. This motor has two stator windings, a main winding and an auxiliary winding, displaced by about 90 degrees. The auxiliary winding has high resistance and is connected through a centrifugal switch that opens when the motor reaches speed. These motors are simple and used in fans and small machinery. 2. Capacitor start motor. In this motor, a capacitor is placed in series with the start winding to create a larger phase shift. This provides higher starting torque. Once running, a centrifugal switch disconnects the start circuit. It's ideal for pumps and compressors. 3. Capacitor start capacitor run (CSCR) motor. This motor uses two capacitors, one for starting and another that stays connected while running. It provides smooth torque and quiet operation. Common in air conditioners and refrigeration units. 4. Shaded pole motor. This small motor has copper shading coils around part of each pole. The shading coil delays the magnetic field on one side, creating a weak rotating field. It has low starting torque but is simple and reliable, used in desk fans or small exhaust fans. All of these single-phase motor types rely on phase shift or magnetic delay to produce rotation. Topic E. Basic motor testing. Now let's move to Topic E. Basic motor testing. Before energizing any motor, you must carry out dead tests in accordance with AS/NZS 3017 and AS/NZS 1359. The main tests are: 1. Visual inspection. Check for physical damage, overheating, or oil contamination. 2. Continuity test. Confirm each winding has continuity and no open circuits. 3. Insulation resistance test. Using a 500-volt insulation tester, measure between each winding in the frame. The reading must be at least 1 megohm, but new motors should show over 10 megohms. 4. Winding resistance balance. Compare the resistance of each winding. For example, in a 3-phase motor, the resistances should be within 10% of each other. 5. Earth continuity test. Verify the frame is properly earthed. If all tests pass, the motor is safe to energize. If not, label it "Do not operate" and investigate before applying power. Applied example: identifying and testing a single-phase motor. Let's finish this part with a practical example. Imagine you're asked to service a small compressor motor that won't start. You disconnect the supply and remove the motor terminal cover. You see 3 leads, labeled C, S, and R for common, start and run. You use your multimeter to measure resistance. Between C and S you read 10 ohms, between C and R you read 5 ohms, between S and R you read 15 ohms. This confirms the windings are correct. The highest reading, S, R, equals the sum of the two smaller ones. Next, you perform an insulation test from each terminal to the frame, all readings above 100 megohms. That means the motor insulation is good. When you reconnect it with the correct capacitor, it starts smoothly. This simple testing method is the foundation for all motor service work. Bringing it all together. Let's summarize Topic 8.19, Electric Motors Part 1. We began with the motor effect, the principle that current in a magnetic field produces movement. We learned about rotating magnetic fields and synchronous speed. We looked at the construction of motors, stator, rotor, and frame. We examined the 4 main types of single-phase motors and how each one starts. Finally, we covered basic testing and saw how to identify motor terminals correctly. Checklist summary. Here's a quick checklist to memorize. Principal field construction type test. Repeat it. Understand the principle, create the field, know the parts, identify the type, and test before use. Summary. To wrap up, motors convert electrical energy into mechanical motion. The rotating magnetic field is what makes the shaft turn. Construction includes the stator, rotor, and frame. Single-phase motors use special starting methods to create torque. Always test for continuity, insulation, and earthing before energizing. That concludes Topic 8.19, Electric Motors Part 1. In our next lesson, Topic 8.19, Electric Motors Part 2, we'll move into three-phase induction motors, star-delta starting, speed control, and motor fault-finding procedures used in the EST exam and in real service work. Welcome back. In our previous lesson, Electric Motors Part 1, we learned the basic motor principles, construction, and the different types of single-phase motors. Now we move into Part 2, where we'll explore three-phase induction motors, starting and protection methods, speed control, and fault finding. Let's begin with Topic F. Topic F, the three-phase induction motor principle. The three-phase induction motor is the workhorse of industry. It's reliable, efficient, and has only one moving part, the rotor. When three-phase current flows through the stator windings, it creates a rotating magnetic field. This field sweeps around the stator at a speed called the synchronous speed, calculated by the formula. Ns equals 120 fp, spoken as synchronous speed equals 120 times frequency divided by the number of poles. For example, a 4-pole motor on a 50 Hz supply has a synchronous speed of 1,500 revolutions per minute. The rotating field induces current into the rotor bars. The magnetic interaction between the stator and rotor produces torque, causing the rotor to turn slightly slower than the synchronous speed. That small difference is called slip. Slip is essential. Without slip, no current would be induced in the rotor, and the motor wouldn't produce torque. For most motors, slip is around 2 to 5% at full load. Topic G. Starting methods for three-phase motors. Now let's move to Topic G. Starting methods. When a motor first starts, there is no back electromotive force, EMF, so it draws a large inrush current, often 6 to 8 times its full load current. To reduce this, different starting methods are used. Let's go through the main ones. 1. Direct online, DOL, starting. This is the simplest and most common method for small motors up to about 5 kilowatts. The motor is connected directly to the supply through a contactor. Full voltage is applied instantly, giving full torque but a high starting current. It's used where the supply network and load can handle the surge, for example, pumps and compressors. 2. Star-delta starting. For larger motors, the star-delta starter reduces starting current. At start, the stator windings are connected in star, applying only 58% of line voltage to each winding. Once the motor accelerates, a timer or relay switches the windings to delta, applying full voltage for normal running. This method reduces starting current to about 1/3 of the DOL value. 3. Auto transformer starting. This uses a transformer to reduce the starting voltage. It allows for adjustable voltage tapping, making it suitable for motors with heavy starting loads. 4. Soft starter. A soft starter uses solid-state electronics to gradually increase voltage during startup. It limits inrush current and mechanical stress, giving smoother acceleration and longer motor life. We'll also discuss VSTs shortly, which perform a similar function but with speed control. Topic H. Direction of rotation. Now let's move to Topic H. Direction of rotation. In a three-phase motor, the direction of rotation depends on the phase sequence of the supply. If you swap any two of the three-phase conductors, the motor will rotate in the opposite direction. So in spoken form. To reverse a three-phase motor, interchange any two-phase leads, for example, L1 and L2, at the motor terminals or starter. Always make sure the motor is stopped before reversing, unless the control system is specifically designed for plug reverse operation. Direction reversal is commonly used in hoists, conveyors and forward reverse control circuits. Topic I. Speed control of induction motors. Now for Topic I. Speed control. The speed of an induction motor depends on two factors, the supply frequency and the number of poles. The formula we used earlier still applies. N equals 120 fp times 1 slip. To change the speed, you can 1. Alter the number of poles, which is fixed for most motors, or 2. Change the frequency, which is what variable speed drives, VSDs, do. Let's explain VSDs in spoken form. A variable speed drive converts fixed 230 or 400 volt AC supply into DC, then back into variable frequency AC. By controlling the output frequency, it adjusts the motor speed smoothly from 0 to full speed. VSDs also provide soft starting, braking, torque control, and energy efficiency. They're common in HVAC systems, conveyors, and modern manufacturing. However, VSDs produce harmonic currents, so filters or shielded cables are sometimes required to protect other equipment and maintain electromagnetic compatibility. So, remember, soft starters limit starting current. VSDs control both starting and speed. Topic J. Motor protection. Now let's move to Topic J. Motor protection. According to AS/NZS 3000 Section 2.5, every motor must be protected against 1. Overload, 2. Short circuit, and 3. Earth fault. Let's go through each one clearly. 1. Overload protection. Overload protection prevents damage from excessive current that lasts too long. This could happen when a motor is jammed, overloaded, or has a bearing fault. Thermal overload relays are commonly used. They have bimetal strips that bend when heated by overcurrent, opening the control circuit and stopping the motor. 2. Short circuit protection. This protects against high fault currents caused by insulation failure or wiring faults. Fuses or miniature circuit breakers, MCBs, are used for short circuit protection. They operate almost instantaneously to prevent cable and winding damage. 3. Earth fault protection. This detects current leaking to earth, which could cause electric shock or fire. Residual current devices, RCDs, or earth fault relays are used for this protection. In industrial systems, coordination between these devices ensures only the faulty circuit is disconnected. This is called discrimination. Together, these protection methods keep motors safe, compliant, and long-lasting. Topic K. Motor fault finding and testing. Now for Topic K. Motor fault finding and testing. Motor faults usually fall into 3 categories: electrical, mechanical, or environmental. Let's go through each type in spoken form. Electrical faults: open circuit windings, shorted turns, earth leakage, or unbalanced supply voltages. Mechanical faults: worn bearings, misalignment, or rotor rubbing on stator. Environmental faults: dust, moisture, corrosion, or overheating due to poor ventilation. When a motor fails to start or hums loudly, always test before guessing. 1. Check supply voltage with a multimeter. All phases should be balanced within 2%. 2. Test insulation resistance between each phase and earth. Readings should exceed 1 megohm. 3. Measure winding resistance. All 3 phases should be within 10% of each other. 4. Check rotation direction and confirm load isn't jammed. Let's apply this in an example. Applied example: diagnosing a humming 3-phase motor. Imagine a 3 kilowatt 3-phase fan motor that hums but doesn't rotate. You isolate the supply, lock it out, and remove the terminal cover. You find that one phase connection is loose and shows a burn mark. You measure resistance. Phase 1 to 2, 5.4 ohms. Phase 2 to 3, open circuit. Phase 1 to 3, 5.5 ohms. That open circuit reading confirms one winding is broken. You replace the motor or send it for rewind, then retest insulation. Now it reads 200 megohms. After installation, you check phase rotation and the motor runs smoothly. This example shows the importance of systematic testing rather than trial and error. When you reconnect it with the correct capacitor, it starts smoothly. This simple testing method is the foundation for all motor service work. Bringing it all together. Let's summarize Topic 8.19, Electric Motors Part 2. We began with the principle of 3-phase induction motors, how the rotating magnetic field induces current in the rotor to produce torque. We learned how slip allows rotation, and how starting methods like DOL, star delta, and soft starters reduce current surges. We looked at reversing direction by swapping two phases and controlling speed using VSTs. We studied overload, short circuit, and earth fault protection under ES/NZS 3000. Finally, we covered motor fault finding and finished with a real example of diagnosing a faulty three-phase motor. Checklist summary. Here's a quick checklist to memorize. Principle: start, reverse, speed, protect, test. Repeat it. Understand the principle, choose the right starting method, know how to reverse, control speed safely, protect the motor, and test for faults. Summary. To wrap up, three-phase induction motors create torque by slip between the rotating field and rotor. Starting methods include DOL, star delta, and soft starters. Reversal is done by swapping any two-phase connections. Speed control is best achieved using variable speed drives. Protection includes overload, short circuit, and earth fault devices. Always test systematically before energizing. That concludes Topic 8.19, Electric Motors Part 2. In our next lesson, we'll move on to Topic 8.20, Damp Situations and Wet Areas, where we'll look at how moisture affects electrical safety, and how to apply IP ratings, protective devices, and installation requirements for damp locations in accordance with ES/NZS 3000 Section 6.